Continuing with simple harmonic motion. So, last time we had a look at some of the equations of the simple harmonic motion. Let's just quickly recap. So we had t equals 1 over f, didn't we?
Yes.
And f equals 1 over t. And t equals 2 pi over omega. Or, of course, the other way to say it is omega equals 2 pi over t. Yeah. And then, of course, we can put in f as well and so on, etc., etc. We also had acceleration equals minus omega squared x.
Force.
And then force.
And then so minus.
Yeah, minus m omega squared x. And Hooke's law, f equals minus k delta x. Or
Just kx without
kx, yeah. I'll write delta x. Yeah, but x, whatever. The extension length. Now, we have really just one more set of ideas to go through. So these formulas are good to find the acceleration and the force. But one disadvantage with these formulas, if you want the acceleration or the force, you need to know what the x is, the position, the extension. We would like some formulas now that only require the time. Okay, so that's what we'll look at first. So for example, I pull this out a distance a, and then it starts to go back and forth and back and forth and back and forth. And I'll call this here O, the origin. So this is positive x and this is negative x. X equals a cos omega t. So that's our first formula. For example, if I put t as 0, what's omega multiply 0? 0. And what's cos of 0?
0.
1. So a times 1 is a. So you can see when t is 0, this starts at a. So that's right. The velocity is equal to minus a omega sine omega t.
How do you get that?
Yes, I was just going to say the proof you need is you need some calculus for it, which we haven't done. So we won't really be able to prove this if you want the proof until semester 2.
Is it differentiation?
Yes, you're right. It involves this. Yeah.
I think everyone here knows differentiation.
Yeah, but I need to pretend as if you don't, in terms of the syllabus. So for the moment, you're just taking this formula as a fact. And then final formula is the acceleration, which would be a omega squared cos omega t. Hang on, something went wrong here. I did minus.
The differentiation of distance is
Yeah.
speed, and differentiation of speed is
That's it.
acceleration.
Yeah. So if you've seen that before, that's great. But if not, don't worry. So this means if I give you the time, you can tell me the position, the velocity, or the acceleration.
Why don't we call distance here s? Right.
Oh, you can. Oh, that's fine. Yeah, if you want to call it s, that's fine. Yeah.
And what's different between x and a?
Well, you mean in terms of value? You see, you have an omega squared.
You know, like x is maximum displacement and a is also maximum.
No, x is a displacement at a particular time. At a particular time. Whereas a, yes, is the maximum x can be. So in other words, to answer your question, you could actually say x is to be between minus a and a. Yeah. So, yeah, x max equals a, big A. Not to confuse with small a.
So a maximum displacement vertically or horizontally?
Oh, either. It depends I mean, if we have a spring on a table, it'll be horizontally, and if a spring hanging from a ceiling, vertically, it doesn't matter. It doesn't matter. But there is a special situation which we'll look at, which is the spring hanging from a ceiling. Okay. So, this is the formulas for x, v, and a. But please note, these are the formulas if you pull and release. It's different formulas if the ball is at rest and you move it by giving it some force so it starts to shake. Okay? This one is if it starts here. But if it starts in the middle, here, and then you hit it and it shakes, it vibrates, you have different formulas. In fact, they're almost the same. The only difference would be, so let's pretend it's here, and then I give it a push this way. Okay? So it's in the center at the origin, and I push it. Let me give it a bit of colour here. The only difference is instead of cos, you write sine. So this is a sine omega t. And here, instead of sine, you have cos.
So is it the same?
Yeah,
Like you push
but
it
there is
like-
no minus then.
Yeah, but we have to fix the sign. Yes.
No, I mean
So-
you push it that way and you go from that
Oh,
way.
you're right. Yeah. In this case here, I'm pushing it to the positive. But you're right. If I push it to the negative, then I just change the signs to make it minus. Yeah. So this one would be a plus sign. This one would be a plus cos. And then this one here would be a minus sign. Yeah. But as you said, if I turn my arrow the other way and it push it to the left, it'll just be minus sine, minus cos, plus sine. You flip them around. Yeah. Huh?
What's the breakdown for plus and
Oh, I'm saying if the ball starts at the center, the origin, instead of at the amplitude, the formulas change very slightly. The cos gets replaced with sine. What?
Why?
Oh, well, if you think about it, what's omega times 0 is 0, and what's sine 0?
Zero.
0. So you're saying at the beginning it is at 0. So this is the reason for the change. It starts at 0 instead of at A.
Where
Yeah.
does it start at the beginning? Start that formula.
Which formula?
Sine, cos.
For sine?
Yeah, the first one that you wrote there.
Oh, the cos?
Yeah.
That it starts at the extreme, at A, at the maximum. You pull it out and release.
Can you show the diagrams?
Yeah, that's it here. Sorry, this here. It's for this one.
So it begins at the plus sign.
Yes. Yeah. And likewise, as Mohammed was saying, if it was the other direction, you pull it to the minus side. Okay. The only difference is this will become now minus plus plus.
Signs change.
The signs change, that's all. Yeah.
I don't understand that.
No. It's fine, but you need to give me a question. So what's your question?
I understood, but I just don't understand where does it start, like from which formula?
Let's call this formulas 1, and this is formulas 2. If it starts here, you use 1, and if it starts here, you use 2. In the center, this is the center of origin.
It doesn't matter whether it's being pulled or pushed.
Oh, it does. So if it's being pushed
From one.
from, oh, but from here, yeah. Well, it can only go to the left because you got to imagine that it's being pulled out. Yeah. What could matter is if it's on the other side, over here. Yes. And in that case, if it was here, all these signs change. Now look. You're worrying about the signs. In the exam, if you got the signs backwards, there's a good chance it wouldn't affect the answer if the signs are the wrong way. What will affect the answer is if you choose sine or cos. Okay? So that's the thing you need to worry about. Don't worry about the signs. Worry about the sine or the cos. So if it starts at the end, we use the cos. And then if it starts at the middle, we use the sign. And look, notice how these change. Cos, sine, cos. And then here, sine, cos, sine. Okay? So you need to remember this. So if it starts at the end, if it starts at the end, what do I need to remember? Cos. So it goes cos, sine, cos. And it starts at the middle, sine, sine, cos, sine. Okay? Now, these formulas are not in the formula book. I know that. Okay? I know that for certain. So these are in formulas that you need to memorize. They're not in the formula book. So please make good notes of them. I want you to write them down. Not in the formula book. The X, yeah, what about it?
These are the formulas we need to memorize because they're not in the book.
Yes.
We memorize only and VA.
If you can, if you're happy, yes, you can. If you're happy with your differentiation, you could just remember the X and then differentiate twice. Yes. Mohammed and Mohammed, have you done differentiation before? Mushtaka? Yes. What? I just said it in Arabic for you. Mushtaka.
No.
Yes.
This is
How do you say? That's not Arabic.
Yeah, mushtaka.
Mushtaka and Tikkamel.
At-takam.
Yeah, Tikkamel. Sorry,
Tikkamel.
Mushtaka and Tikkamel.
Yeah,
Have you done
Tikkamel.
this?
Yeah, I've done it.
Yes.
I never did anything.
You never did this.
No, I never did
Mohammed
anything.
S? Have you done this topic? Yes.
Yeah.
Yes.
Tikkamel.
Tikkamel. Mushtaka and Tikkamel.
Tikkamel.
Oh, that's so different. I'm so sorry.
Yeah.
I now understand why you did not understand
Yeah.
anything I was saying.
Yeah, it's a mushtaqat and tikkamel. Yeah.
You haven't done it, or
Yeah,
you
it was
have
like high school back like 2 years.
too long ago. Okay. Did you write that down? Yes. Not in the formula book. Okay. Let's have a look here. Okay. Let's do some examples now. Yeah.
So 2 is from the origin.
Yeah.
2 is for the origin. Any origin.
Yes. Okay.
Are any big things in the syllabus for further maths? Not exactly for simple harmonic motion, but still deriving the formulas for E and A.
Yes, they are. Yes, yes.
Why do you have to move on?
I don't know. I'm just a maths and physics teacher. Talk to someone above me, like
But you told me that you were a further maths.
I was a further maths teacher. Not simple, not enough demand for it.
But then you got an error in
Huh? What? What'd you
the
say?
You got an error in
I have it now? What do you mean? No? Alright. Maybe it's better if I don't know. Yeah, well, there's reason for no further maths is because there's not enough demand for it. You know? Like, maybe last year only one student wanted to do it.
Most of the people who are sitting in this room want to do further maths instead of chemistry. Yes.
Okay, but like I said,
Yeah,
What's your best choice? I would prefer
that's fine. But the thing is, you need to let the people above me know.
But when we were making our applications, we included the information that we want to do physics, math, and further maths.
Everybody said this?
Yes.
I said no.
Okay. How many people picked further maths? 4, 5.
Right, you know what?
Don't put up your hand if you don't know what you're saying. Huh?
How many people picked or wanted to?
Yeah. Oh, no, pick on the application. Yeah.
The case math,
Yes. You prefer? Yes. Okay.
That's what he's saying.
I don't know, having a choice on the
Yeah. Okay. Well,
It's too late anyways.
possibly. Huh? Yeah. Well, like I said, you must view me as a simple maths and physics teacher. I have no power to make any changes.
Well, you could err of opinions.
you are assuming my opinion counts for something. Yeah. All right, let's go on now. Okay, can I scroll down? Yep. So this next example is a little bit difficult, so you have to watch carefully. So what we have,
That's what you just said now, okay? Oh no.
I'm just going to continue now. So what we have is a spring here, and its length is L. This is called its natural length, the length at rest. So L is the natural length. Do you know what I mean? Natural length, the length at rest. Then what you do is you put a mass here of m. So what should happen when you put the mass on it? Well, then it will stretch down. L plus delta x, and here is the m here. It's moved down delta x. Okay. I would like to calculate how far it has moved. What's the distance it's moved? How can I calculate that? Well, first I should draw the forces, yeah?
Yes.
So what are the forces going down? Mg. And what's the force going up?
Yeah.
Tension, true, but from Hooke's formula, what is the formula?
Who's what?
Yeah,
Yes.
K
K
delta x.
Oh,
But you're right, it's the tension.
since we're using L, shouldn't it be delta L?
No, L.
Oh, you mean, no, he just means notation-wise, yeah?
Yeah. So people get crazy same thing.
Alright, fine. It wasn't confusing me. Delta L. Make Joshua happy. Delta L. Okay, so we can say K delta L equals mg. Therefore, delta L equals m over kg. So that's the extension. So, if you make the k bigger, what happens to the extension? It gets smaller. And if you make the mass bigger, it gets bigger. Yep. Okay. Now, next. So continuing with this, let me make some space.
This formula is for any case.
Here?
Spring.
Oh yes, yes, yes. Not just a spring, but yeah. Okay. So now what I do, please note, there's no mass here, okay, and then I attach the mass. Then here it's at rest. It's not moving, okay. Then what I do is I pull it down a distance a. And what I'm going to do is I'm going to call this here the origin. And this length here is L plus delta L, which is m over kg. That's this length here. This is the origin, 0.
The origin is what?
I'm calling the origin here a distance L plus delta L from the top. In other words, Joshua, the origin is where it would be if it was at rest, the 0. I'm calling that 0.
So why are we calling it 0 when there's mass attached?
No. I'm calling that location the origin. And the reason for that is it'll make the following calculation easier to do. That's the reason why. Okay, so what is the force that goes down on this mass here? In this picture, what's the force down? Mg.
Plus.
Yep, that's it, force down. Now the force that goes up, though, this force here, what law do I use? Hooke's law, which is K, and then we need the extension.
L.
Yeah.
The mouth is dragged down.
Yeah, pull down. Yeah.
So how
extension is E.
Oh, okay, hang on, we need to go back a step, yeah. Right, can we all listen carefully so we have the right picture in our minds here, okay? Look up. So this spring has no mass, okay? Then I put a mass on it. What will happen? The spring will move down to here, where it's at rest, and it will just hang, okay? Then I come along and grab it and pull it down more. And then I release, and what will happen? It goes up and down. So here it will go up, down, up, down. Yes? Is that okay now? Yeah? Now, this is changing. So we need a different letter. I can use X or I can use S. Since we've freed up X now, L now. Sorry, we freed up X now, I'll call it X. So this here I'll call X. So for example, what's X when the ball is here? A. And then when it's here? 0. And then here? Minus A. Okay? So the X is changing. Right. So what is the length? The length is L plus mg over K plus X. Can you see why? Because it's this distance plus the X. That is the total distance. Yeah, which at the beginning, as you pointed out, Joshua, is big A at the beginning. You're right. Minus L. Now, who can tell me why I need the minus L there?
Yeah, it's because it's the origin. It's where there's no force.
Yeah, or in other words, you're right. It's the extension that you only use in the formula. So you need to minus the L. But that's good, because what happens there then? You see the L's cancel. So you're left with this now. The force going down equals mg, and the force going up, well, that will cancel with that, and that will make mg. The k's cancel, don't they? Plus kx. Now, if I scroll down a bit, let's draw our situation. Here is the mass. Going down is mg, and going up, mg plus kx. So, therefore, this is the same as up kx. Because the mg's cancel. Okay? So we can say, let me zoom out more. Can we still see? We can say t, if I want the time here, what's the formula for that? I think I gave it to you. Yeah, or 2 pi over omega. So we need to find the omega, don't we? Sorry, I feel like I left out an m somewhere. Here. Okay. No, I didn't, sorry. Okay. I'm going to find the omega now. Right. Now watch carefully. We have some formulas for the force, don't we? The force. Give me the formula for the force that I gave you last week. What's the formula for the force?
Minus g.
Yeah. Now since it's going up, we'll say plus. So it's m omega squared x. These are the same. This is the formula for the force, and this is the formula for the force. So they're the same. It's the same force. So I have kx equals m omega squared x. So the x's cancel, and I get k equals m omega squared. And now I have my result. The omega equals square root k over m. So now if I want to know the time, what's the formula for the time? 2 pi over omega. So that will be root m over k. So this is the result I was trying to get.
So I'm confused with the negative.
Oh, the signs again. Which way is this ball going? No. You answer me.
Alright.
Which way is this ball going? Up or down?
In that case,
In my diagram.
alright, it's up.
Oh, and up is positive or negative? Now look, it's fine. If you call it negative, it's absolutely fine. But then that means on the other diagram, you have to call that minus kx.
Yeah.
But there's no problem there. That is not a problem. This is the formula I wanted to get. This is the formula for when you have a spring and it's bouncing. The time for one cycle is this. Now, I want you to think very carefully. I have my spring, I pull it, and it goes maybe 1 second. Okay? Now, same spring, and I pull it much more, and I let go. Would it be more or less than 1 second?
Less than more.
The time, more or less?
Less.
No, the same. The same. Because look at the formula. Is the big A in this formula? No. What's in it? The M. Is the M the same? Yeah. Is the K the same? Yeah, it's the same spring, isn't it? So you see, that's a very unusual result. That it does not matter how far you pull it. That the time only depends on the mass and the K of the spring.
What about the speed?
The speed will be different. Yes. But I'm just talking about the time. Yeah, of course, because if you pull it, but this is the thing, if you pull it more, it'll be going faster, right? But it has a greater distance to travel, and the two cancel each other. Yes. Yeah. So this formula here is an important formula. It's in the exam. Yes, it's in the exam. But I don't think this one is. I'm not sure. I don't remember. But I've seen this one in the formula book. Yeah. Question, Joshua?
If you do distance over speed.
No, because that is only for linear motion with constant acceleration. This acceleration is changing. Yeah. Okay, did you write that formula down? So that's important, okay? Right, so we have another formula to prove now. And the reason I'm doing the proof, this proof is not going to be in the exam, but the reason I'm doing the proof is it's good practice of the formulas. Okay? Now the next proof is very important. Okay, I'm going to say this, so listen carefully. This next proof is very important because you have to do a lab report. And as part of the lab report, you need to include this proof. So the proof I'm going to do, you will need it for one of your lab reports. In fact, I think it's lab number 1. Okay? So last year, the students lost that proof because they didn't keep good copies of their notes. Alright, so don't lose this proof. You need to include it in your lab report. The next proof. So I'm going to do it now. Okay. So for this proof, this is the situation we're looking at. Now, this is also simple harmonic motion because if you think about it, this is going left and right. Yep. So the motion is like this. I mean, it's not perfectly a straight line because it's curved. Okay? But it's still this motion like a spring. So this makes us think that maybe we can use the same formulas but for this situation. So we need to get these formulas. So firstly, some information. So let's just call this one here M. and I'll call this here L. Okay. Now, and I'll call this here theta.
It's in the wall.
No, that's just marking where I'm measuring the angle. Okay, let's draw in our forces. So, our first force, of course, is here, which is mg. And our second force, which is here, which is T. Now, if that's theta, then what's this angle here? That's also theta. So, is this one here cos or sine? This one. T cos theta. And then this one here is T sine theta. Okay. What does this word mean? Approximation. Yeah. Almost. Roughly. Rounded. Yeah. You know and I know this will not travel in a straight line. It will travel in a curve. But we need to approximate. We need to say it's roughly a straight line. Do you understand? We're not saying it is a straight line, we're saying it's roughly a straight line. But we know it's not. Okay? So if it's traveling in a straight line like this, look, like this, then we know that T cos theta will equal mg. Yeah, that the up equals the down. And then T sine theta does not equal does not equal 0, because it's the T sine theta that makes it go to the left. So this makes it go left and right. Now you need your calculator for the next bit. So can you take out your calculator? Okay, so can you change 5 degrees into radians? So if you remember, what did I say? You divide by... No, sorry. Yeah.
1/36
Yeah, it gives me as a decimal.
0.0873.
Okay, 0.08 we'll just say. So 5 degrees is 0.08 radians. Now, if your calculator is still in radian mode, type in sine 0.08 and cos 0.08. So this one here
is 1.5 times 10 power minus 3.
Oh, okay. Are you sure about that?
No, it's 0.0.
No, you're not in radian mode.
0.0799.
So 0.08.
Yes.
Yeah. And then cos. See,
0.99.
the problem is you're using that calculator. 0.99. So that's roughly 1. Yes? Now this is the point I'm making. No, look up. If theta is small, you have sine theta is approximately theta, and cos theta is approximately 1. If theta is small. And you can see that with an example here. Okay? So this is our second approximation. That if the angle is small, we don't need a calculator, we can just use this result. Okay, so you need to write that down. Because in your lab report you need to explain all this. Okay, so note though that sine theta is approximately theta and cos theta is approximately 1. So if I use that result now,
Approximately theta.
yes,
0.
Yeah, so we'll just leave it
Huh? I don't know what you're talking about. So here we get cos, not cos, sorry.
Excuse me.
Yes.
What do you mean by sin theta approximately theta?
Oh, that, no. I know that sine of 0.01 is approximately 0.01.
Okay.
Sine 0.02 is approximately 0.02, etc.
Is that what this example is?
Hmm?
Is that what this example is?
That's the point I'm making with this example. That you don't actually, look, you don't really need your calculator. If I type in sine 0.02, I know the answer should be roughly 0.02. And you can see it is. Yes?
What range of values can we take theta?
Good point.
But that's thinking like if theta was small,
Yeah, that's what he's asking. I think 5 degrees, maybe up to 10 degrees, but it starts becoming, like less than 5 is great. But once you start going past 5, you start to see the error more. 5 degrees, maybe 10. Definitely single digit.
So more than 5 it's a bigger degree.
Bigger error. The approximation is not as good. I mean, if we look at 10 degrees, so that would be 0.16. Sine 0.16. That's actually still 0.16. It's 0.159. So it's actually still good to 2 places of decimal all the way up to 10 degrees. So yeah, between 0 and 10 degrees is fine.
So in this part, we use radians in this part.
Yes, radians. Yeah. Now you can use, in the lab report, you can use degrees and radians. Or you can use degrees and then convert to radians. I don't mind too much. But for the proof, you definitely need radians for the proof. Okay, I'm going to continue now. So, using that result I've just talked about, we can now say that T is approximately mg, and that here we have the force. So let me just, fix that. I'll just call this here the force that is moving it. The force is approximately T theta. So if I put these together, I get the force is equal to T theta, but T is mg, so that's mg theta. From Newton's second law, what's the formula for force?
F equals ma.
Ma, yeah. So Ma equals mg theta. Oh, by the way, guys, Tanish, before you ask me, I really should put in a minus because it's going to the left. So I'll just add my minus in here, okay? But again, not necessary. I'm just making the point that it's swinging to the left here.
And then cancel.
M's cancelled, so we get A equals minus G theta. Okay, so we're getting there. Now, we need to find something about the A.
You could change theta to minus T.
We're getting to that, yeah, but not quite there yet. Now, this here is a bit like the X. So X starts big, and then in the middle, what's X? 0, and then it goes negative. I would like a formula for the X. Yeah?
A is acceleration, G
Yeah.
is
A is the acceleration to the left. Yeah. Okay, so if I look at this triangle, the hypotenuse is L, the opposite is X. So I could use here opposite and hypotenuse. Which one's that? Sine. So what does sine theta equal? X over L. But remember, what does theta equal, or sine theta equal? It's roughly theta from here. So again, so we get theta equals X over L.
So how do we get sin theta equals X over L?
From trigonometry. Sine is opposite over hypotenuse. Okay. Now what I do is I put this result in here, and I get A equals minus G x over L. So I get A equals minus G over L x. Now, I gave you a formula last week for A. What's the formula I gave you for A?
Minus omega squared.
Yeah, so here we have but A equals minus omega squared x. Therefore, putting these together, I get omega squared equals G over L. By just comparing. A equals minus a number by x. A equals minus a number by x. Therefore, these must be the same number. So, a square root and I get omega. Okay, nearly finished. What's the formula for time? 2 pi over omega. Yes? So that means t equals 2 pi root L over G. I would hope so. It's one of the, key physics formulas. So, we're in this situation. If I know the length, then I know how long it takes to swing back and forth. So, on your calculator, I want you to make the length 1 meter. 1 meter. Tell me the time it takes to swing back and forth. I want you to do that now. Question? No?
This formula is for flow, for tension in the
Pendulum.
2 seconds.
this pendulum.
2 seconds. Good. Now, make the length half a meter. Should the time go up or go down?
1.4. 1.4.
1.4
1.4.
seconds. Okay. So my next question then, are you listening? If the time is 1 second, for example, if the time is 1 second, tell me the length. Now you have to work backwards. So the time is 1 second. I want the length. Now, while you work on that, I need to get some expensive equipment. So,
0.25.
you have it?
Yeah.
All right. I need to get some expensive equipment. Okay, so just wait there and I'll bring it back. And we're going to do something with this for the lab report. Expensive equipment. You think you know what I'm going to bring?
Yes.
Yes, expensive.
It's not expensive.
60.
Nah, shit, it's sorry.
expensive equipment is back. Yes. All right. So.
I don't think you're a historical family.
Yeah.
Samurai.
It's like being back in China, isn't it? Ah. Now, what length do you need for the time of 1 second?
Oh, 0.25.
0.25, yeah? All right. Stupid Americans, that's it. No, it's inches. Okay. Now, we calculate it would take 1 second to do this. Yes?
Yeah.
So, 10 of these will take
10 seconds.
10 seconds, yeah? That's 25 centimeters. Take out your stopwatch on your phone. Stopwatch?
Yep.
Yeah, you know stopwatch? Yeah.
Okay. Go ahead.
What's the
What?
Go ahead.
Yeah. So, we think, hey, we think it should take,
Take 1
One
second.
yeah, it's this piece here. Okay. So we think it should take 10 seconds for 10.
Yeah.
Yeah. So what I'll do is I'll count 10 and then tell you when to stop, and I'll tell you when to start. Okay, you ready?
Yeah.
Yes, ready? Okay. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
Yeah, 10.
Yeah,
Exactly.
exactly.
Wow! Oh my God!
Same as him.
Plus
Yeah.
So amazing.
Physics. So
because it took like it was
The work.
it's going to take
It's
like 0
awesome.
seconds per second.
I got
You didn't know.
Oh,
Present. Present here.
amazing.
dang. You don't get that in biology class.
You can do the zero.
Yes. Yes, amazing. Now, why is this important? Because what we do in the lab is we time this and we use the L and the T to find G. Okay, so for example, this was 25 centimeters. And what was the time for 10? 10 seconds. So what's the time for 1? 1 second. So we put T as 1, we put L as 0.25, and we calculate the G. So this is how you calculate G, using this. Yes. Mhm. Now, it is important though, because this is how it was originally done. And the better you can make the pendulum, and the more accurate you can make the clock, the better the value of G. But there are some problems. So what would be possible problems with this?
It will stop.
Yeah, I mean, it doesn't continue. It slows down.
Yeah.
That's one problem. Another problem?
Wait.
Air resistance, yeah.
On your head.
Yeah, so it shouldn't be my hand. So in the lab experiment, you'll have a little clamp. You can clamp it onto that. Okay. Yeah, and we don't have that. That's actually too expensive. I just got a small clamp. They are surprisingly expensive.
You can do it by yourself.
Yeah, yes, yes. What else is a problem?
Grab the 3 cheat sheets.
No.
And that's the thing.
You're right, the string is a little bit elastic. This is a problem. Yeah. And anything else?
The ball itself.
Yeah, how so?
The material.
Yeah, but how's that a problem? What's the
The
problem?
weight.
Huh?
No, the weight of the ball.
Yeah, no, measurement error. How? Well, look, when I say start, there's a slight.
The length of the rope,
Oh yeah, that's fine. Yeah, the length. Yeah, it's similar to what Mohammed was saying because it's a little bit stretchy, or just simply measurement error. Or again, when you say start, there's a small error, time delay.
Everything is fixable.
But everything is fixable. Everything can be improved. And anyways, what you do in the lab is you do this for 10 different lengths and get 10 different measurements and get the average. Yeah,
Do we calculate the uncertainty?
yeah, you do that as well. Yeah.
Do we use different months?
Hmm?
Different months.
No, 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 no. It'll just be this. that and the stand. Expensive, yes. Yeah. The most expensive thing actually is the box of weights for Newton's law. It's like a box of 10 weights, you know, like 5 kilograms, 1 kilogram. How much do you think that would cost, a box of 10 weights?
€10.
100 euros. Yeah.
That's why we don't do any electricity experiments. It's
No. The electricity one was the cheapest. It's extremely cheap.
Ampemeters, voltmeters.
Yeah. I got multimeter for 15 euros.
That's
So I got 2 multimeters. That's 30 euros. I got a resistor, a pack of resistors for $1. I got the cables for $2. Yeah. No. All right.
That's cute.
Yes, isn't it? I can just about no. Okay. So did you write this proof down? It's important for the lab report.
Well, it's very much
Yes. Hence the writing down of the proof. Yeah. Okay.
You need to remember it, so just write it down in the lab report.
Uh,
It's not good.
Now.
Will you come on the exam?
Huh? Yes.
No,
Yes.
proof will not.
No, not the proof. No. Now, there's some things you can do with this proof to make it a little bit easier to use in the lab report. So, we should square this. We get t squared equals 4 pi L over G. 4 pi squared, thank you. L over G. And I can rewrite this. No, actually, I can leave it like this. T squared equals 4 pi squared over G times L. So if I draw a graph with t squared here and L here, that means this is the y, and then the L is like the x. So this piece here would be like the slope of the graph. Should go through the origin there.
Yeah.
So what you do in the lab is you do 10 different measurements, you draw the line, you calculate the slope, and then you use the formula slope equals 4 pi squared over G. So then you get G equals 4 pi squared over the slope of your graph. So that's what you would need to do.
And we'll need to find G.
To find the G, yeah.
So this would be the purpose of the lab report.
Yes, the purpose of the lab report is calculating the G. So you should get a slope of approximately slope of approximately 4. Yeah. Your slope should be roughly 4, like 3.99, something like this. Yeah. If it was actually exactly 4, then your G would be 9.86.
9 point. If it would 4.02
Would make it exact.
Would make not exactly, but
Okay. Yeah, close enough. So roughly 4. Okay.
But if we will not get it wouldn't affect the grade if we would have that measurement, but we'll have everything written down.
Oh yeah.
And we will calculate the errors. And
Oh yes. There's a tolerance.
Yeah, okay.
So if you came out with an answer like G is 11, no. But if you came out somewhere between 9.5 and 10.5 even.
But what if you had G is 11, but the lab report in itself is perfect?
No, that wouldn't. See, you do get marks for how accurate you were. So there are accuracy marks. So that is important. You should try to be accurate in the lab. Yeah? Yes?
How many marks is the graph?
Don't worry about that. I'll give you a detailed breakdown of the marks for the lab report before you start. So yes, you'll see how many marks are for the graph, how many marks are for the calculations, all this stuff.
So we will be doing the lab report on semester 2 also.
Lab report starts in semester 2. Yeah. What's wrong?
Why is it great? But we have reports.
Okay. Yeah, the physics, 4, 4, 4, 8.
4, 4, 8. Or 4, 4, 4.
3 4s and an 8.
Oh.
Yes.
4, 4, 4.
This one is 4%. Okay.
What's your remaining time?
The end of semester 1 exam.
Oh.
Okay, can you go to page 77 now? Come on, 77. Okay. Okay. Now, I want to draw a graph for you. So, if we think for a moment again, back here. This, we said, is simple harmonic motion going back and forth, okay? So, again, like with the spring, it'll be going back and forth like this. So I want to talk about the energy. So imagine I have the spring and I pull it all the way out and hold it and then let go. It will fly in. Yeah? So when I pull it out all the way, what's this distance called? Yeah, but when it's at its maximum? Amplitude, big A. Will the kinetic energy be less than, equal to, or greater than 0 at this place?
0.
Yeah. Be 0 because,
It's high maximum potential.
yeah, it's not moving by maximum potential. So, if it starts out here at the A, the kinetic energy will be 0. Then, as the x gets smaller, what happens to the mass? It gets faster. Think about it. If I pull it out and let go,
Yeah.
the x is getting smaller as it moves, but it's going faster. So what does that mean for its kinetic energy?
Going bigger.
It's increasing. So the kinetic energy will go like this. Then this is at the origin, 0. Then when it passes the origin, it starts to slow down until it hits where? Minus A. Okay, so if you look, starts here, no kinetic energy, faster, 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 more kinetic energy, then it passes the origin, slows down, no kinetic energy, and then starts to fall back. Huh? Yeah, so actually you could think of the spring as on the x-axis. So when the spring is pulled out to A, it has no kinetic, and then I release it, it flies back to the center, gains kinetic, and then passes the center, loses kinetic. Yeah. Now,
What about potential?
the energy for potential is the opposite. You can remember when the ball is up in the air at rest, it has no kinetic, but it has lots of potential. Then I let go, it falls, hits the ground, it has lots of kinetic, but no potential. So they're always opposite. Yeah, so it'll be the other shape, upside down. So this red one here is the kinetic energy, and then in blue is the potential energy. So here's potential. Then it falls down. No potential in the middle because the spring is relaxed. And then all the way back here. So in blue is potential energy.
Can you pick just 2 lines like that? Or like that?
No, it is a curve. No, it is a curve.
That doesn't it change like linearly?
Yeah.
It does not.
So
It is a quadratic. It is exactly a quadratic. And you can see this in the formula in a moment. This graph has been on the exam. What they've done in the exam is they've given you this graph and they asked you to label parts of the motion. So for example, the question might, the graph question might be something like, draw the kinetic and the potential energy graph for the spring. So then you draw this. And then part 2 might be, label on the graph where is the maximum kinetic and the maximum potential. So where's the maximum kinetic? The top, very good. And the maximum potential? The two ends.
Yeah.
That's maximum potential, yeah. So that's been in the exam as a section A question. Yep.
In some diagrams, the maximum it can be at E.
Yeah.
And
The maximum kinetic is at the top there, yeah? And the maximum potential is the two endpoints.
Will you give us any past papers for the midterm exam? The one which is right after this spring?
Maybe, yes, we'll talk about that on Thursday. Yeah. Okay, so that's the energy graph for the spring. Okay. Now, you actually have formulas. So, the first formula is not interesting. You know it already. What's the formula for kinetic energy? A half mv squared. There's nothing useful there, really. And that's still true for the spring. But the potential energy formula is different. It's not mgh, because that's not what's happening.
Half amigus squared.
Minus
Yes.
G and then
Hold on there.
I'll show you this.
Hold on. It is a half kx squared. Yeah. The potential energy is a half kx squared. So that's why, Tal, I said it was definitely a quadratic, because this graph here, that's it there. That graph is a half kx squared.
Can we write kinetic energy using x?
Yes, you can. You can. Well, one way to do it is, you know that potential energy plus kinetic energy must equal a constant. So you could actually just do it as constant minus a half kx squared. That's one way to do it. Another way to do it is you could use your calculus. You can replace the v with, and so on.
So integrate v.
Yeah. But I wonder what they do in the book, actually. Let me see.
I think they integrated it.
Is that what they do in the book?
Probably. Yeah, because they got, I don't know.
No. Okay. Yes. No. In the book, hang on. In the book, they leave it like this. So they keep it like this. But in the book, they also change this. They write it using omega. So you have your formula for omega. What's omega? Root k over m, wasn't it? Yeah. So if you want, you can write it using omega. But I'll just leave it with the k. Now, just before 1 second, I need to say this is not in the formula book. Yes, you're right.
If we're given different values to find potential energy, can we also use half
A
of
half fx.
force.
Yes.
F as force.
Oh, as f as force. Yeah, because force equals kx. Yes, so that's fine.
Can we use the formula for v that you get in
Oh, yes, you can.
And then
What?
just
Yes?
the one which is a omega sine omega.
Yes,
t.
absolutely.
And
Yeah.
then,
Yeah, just to be clear, because a couple of people have asked me this. These formulas are 100% compatible with the formulas I gave you last week. So, as Tal was asking me, could you use the formula for V in there? Yes. You were asking me, could you use the formula for force in the second one? Yes. Could I use the formula for omega in here? Remember, omega equals root k over m? I can. Okay? So this is just the basic formulas, but in the exam, you might have to get some information from another formula and put it inside of this one. In fact, most of the time in the exam, that is what you're doing. It's unusual in the exam that they just give you all the information and you use one formula. usually what happens in the exam is they give you information, you put the information in one formula, you get the answer, and then you put it into another formula, okay? Maybe there might be one or two short questions that just use one formula, but 90% of the time you need two formulas. Okay, so for example, part 1 might be calculate V. So you, as you said, Tal, V equals the A omega cos omega t. And then part 2 of the question could be maybe calculate the force. And then part 3 could be calculate the kinetic energy. Part 4 could be calculate the potential energy. And then maybe part 5 would be calculate the total energy, which would only be 1 mark because it would be kinetic plus potential. So it's simple.
Total energy doesn't have any.
No, oh yeah, that's a separate formula which I'll do in a moment, but I'm talking about total energy as in kinetic plus potential. Yeah. Okay. Which you've gotten to the result down here. I won't do the proof because it uses calculus, but as you've spotted, Mo, if you calculate kinetic energy plus potential energy, that will equal a half mv squared plus a half k x squared. So this is the total energy. And like I said, I'm not showing you the proof, so I'll just write dot, dot, dot. But these can actually simplify, and it's actually at the bottom of page 77. You can simplify this into a half m omega squared a squared. That's if you use the omega.
R squared that they have is A.
Yeah.
So, okay, now I understand.
What's that?
How did you get omega squared?
No, what? Tammy, I just said with my dot, dot, dots, I'm not doing the proof. I did say that, didn't I? Yes. I'm not doing the proof, Tamish. I'm just giving you the result. That you can put those two together, you do some algebra, and you get this result at the end. Okay? Now, I don't like the omega in it. Yes, so I want to get rid of the omega. So what formula can I use? Omega equals root k over m. So let me just get rid of that. Isn't it root k over m or m over k?
Which one are you going?
Omega.
Pendulum or spring?
It's the same for both, actually. Yeah. What is it? Omega is root k over m. And then this is squared, and then this is a squared. So I get E equals a half k a squared. Do you feel a sense of relief, is it, that this has reappeared? I prefer this formula because it needs less information, or it doesn't need much information. So this is how much energy is in the spring. Now, notice that the A is squared. Okay, so just think, I have a spring and I pull it. And then if I make it twice as long, I have 4 times the energy in the spring. Because of the square on the A. Okay? So, my spring, let's say it has 100 joules of energy. If I make it twice as long, it has 400 joules. Okay, because of the square on the A. So if I want to know how much energy... If I want to know how much energy is in the spring, I just need this formula. Now please, remember, this is the total energy. This is the kinetic energy and the potential energy. It's the total energy. Kinetic and potential. Okay? What information do you need to know about the spring to calculate its energy? You need to know the A, which is the amplitude, and the K, which is the spring constant. Yeah. That's all you need to know for the total energy. Yeah.
For total energy, we need just A.
And, well,
Oh,
K.
yeah.
And like I said, the proof I won't do with you. not that it's complicated. It's just we haven't done the right chapter in maths yet to do the proof. And anyways, it's not a proof that's on the exam. It's not a proof in the lab report, so it's not an important proof. Okay. How are we doing for time, actually? Oh, loads of time. No.
20 minutes.
17 minutes.
18.
I have some more vocabulary to do with you.
Maybe we know it already.
Well, that's great. It'll make it easy for everyone. Okay. Next. Okay, did you write that formula down? Yes? All right, so some vocabulary. So, when this is going back and forth, that's just called oscillations. But if it's going back and forth and it slows down, yes, that's called damped oscillations. So it's important that you know that the formulas I did with you only work for normal oscillations. They do not work if it is damped.
Okay, so we're going to do formulas for damped.
No.
Down to station.
But it's good to have this vocabulary because in the exam it might say it is not damped or it is undamped. Okay. Right, next. Okay, can I scroll down? Yep. Okay. In chemistry, you have done bonds. So, what bonds have you done in chemistry? Covalent, ionic,
Hydrogen.
and then is there van der Waals or something
Yes.
like this? Yeah. Now, have you done the difference between solid, liquid, and gas?
Yeah, from this.
Yeah, we know.
You don't. Okay. So, what happens when you heat something up? What happens?
Gases. Melts and then
Yeah, the bonds they break, don't they?
yeah.
Yeah. So, when something is solid, the bond is quite strong, and then when it's gas,
Where we just
it's weak. Yeah. So I want you to picture a solid substance. The molecules, they're not moving too much, but they are still moving a little bit. They're vibrating. Very good. Now, is this something you knew from middle school, or is this just something you did in chemistry? You knew it. Okay. So these are vibrating back and forth. And in fact, the type of motion is simple harmonic motion. So let's imagine that each of these are vibrating with omega. What is omega? What's the unit? Radians per second. So the bigger the omega, the faster it's vibrating. Okay? Is that okay? Yes? Yes? Okay. Now, if we think back for a moment. So do you remember the example earlier I did with the spring? So if I pull the spring down, it starts to vibrate. Yep. And then if I pull it down more, it vibrates still. But is the time the same or different? It's the same, isn't it? Now tell me this. Imagine I have the spring like this. Yeah, we need to imagine. So I have my spring and it's vibrating up and down. And the time is the same. Even if I pull it down more and it vibrates. So what about if I do this? If it's vibrating and then I come along and I start doing this at the top.
It's another approach.
Yeah, another force, yeah. Yeah, so it's going up and down, and then at the same time I'm doing this as well, so it's going up and down as well.
Is it down? Isn't it down so?
And we'll say it's undamped, that there's no air friction.
Like the ball and the ball.
Yeah, but let's just keep it simple. It's a spring, it's going up and down, and at the same time I'm doing this to it. So, I want to know, will that make the time bigger, smaller, the same, or you don't know, or what? How does it affect the time?
I think it's still the same.
You think it's still the same? Yeah, anyone else?
Time
Sorry?
of what?
The period time.
Of which of those?
Oh,
estimations?
the spring always goes
Slow.
up and down.
This is
Going faster.
Faster, slower, the same. It's the same actually. It's the same. Now that's strange. If this takes 1 second, and then I come along and start to shake the top of it, it still takes 1 second. So it is very difficult to check. Yes, it's confusing, I know. It's very difficult to actually change the time. The only way to change the time is to change the spring or change the mass. Okay? But something does change though. What does change? Well, the amplitude changes, okay? Because if this is going down and then I go down at the same time, it goes down more. This is an important idea. It's the same here, okay? I have all my molecules here in the table. And if I shake the table, the omega does not change. But what does change? Amplitude, which means the molecules move more.
If you
Okay.
check it hard enough, the table will break.
No.
So the amplitude will become very big.
Not if I shake it hard enough. No.
Faster,
Huh?
faster.
Not fast enough, no. Now watch. So here is my material. Okay, so it's shaken with omega. And then I come along and I shake the table. So I shake it as well. So I call this omega 1 and then I shake with omega 2. So if I shake it, what did we say happens? The amplitude gets bigger. But is it still omega 1?
Yes.
Or is it omega 2? It's still omega 1. Now, we have some situations here. Omega 1 does not equal omega 2, and then omega 1 equals omega 2. This is actually different. If I shake it with the same omega as the table's molecules, I make the amplitude really big. So in this situation, this makes the biggest change in amplitude, and then it will break.
Resonance.
Yes, that's the word, resonance. Yeah. So what I'm saying is, let's imagine the omega for the molecules is, I don't know, 1 radian per second. Okay, so the molecules move in 1 radian per second. So then if I shake the table, move.
Yeah.
Yes, all this, yes. So if I shake the table at 1 radian per second, this makes the biggest change in the amplitude of the molecules. Okay? This is the most extreme vibration for the table. Yeah, you see that's kind of strange because you might think, oh, if I want to break the table, that just means I should shake it harder. No. If I want to break the table, I should shake it at the same frequency as the molecule's vibration.
So if you do more than that, it will work.
No, I mean, if you shake it hard enough, it will still break eventually. But it's not the most efficient way to do it. You can do the breaking with a lot less energy if you just match the frequency of the molecule.
Is that the secret of the gas drinking break?
It is, you're right. If you've seen that video on YouTube of the people breaking the bridge, so on the bridge there's a little hammer, and the hammer hits the bridge, and the frequency it hits the bridge is the same as the molecules of the bridge. And as you watch the video, you see the bridge starts to shake a little bit, then it shakes more, and then it collapses. Because the frequency was matched with the molecules. So it makes it the quickest way to break it, the most efficient way. Okay? It's the same when you have the people who sing and they break the glass. The glass did not break because they sung very loudly. The glass broke because the vibration matched the vibration of the molecules. And you might say, how does the person know who's singing what frequency to sing at? Well, if you've seen it before, what they do is they take the little fork No, and then they hit the glass, and they hear, and then from that they know what sound to make to break the glass. So it's not breaking because they're loud, it's breaking because they match the frequency. The glass starts to shake, and then it breaks.
The glass is not shaking right.
I know what it is, the molecules inside it are. You know this from chemistry. There is only one situation in which the molecules do not move. What's that? When?
Minus,
Minus 273
Absolute
degrees. Yeah. Absolute zero. This is not at absolute zero. Absolute zero is the only time molecules do not move in a solid.
And so resonant doesn't work.
And resonance could not work. No. But
nothing works.
yeah, things don't work properly then. But as long as it's not at absolute zero, it means it's vibrating. And if it's vibrating, you can match the frequency.
What if it's negative 271?
Still, it's fine. Yeah.
Nothing but very, very.
Yes, you're right. So you probably need a very slow shake to do it. Yeah? Yes. Okay. So there's a word that describes this, and it's actually on page 78. So this is called resonance. This is very, very important for the engineering students, particularly when it comes to bridges. Okay. So, for example, when I walk, what would you say my frequency is for when my foot hits the ground? So, what would you think? Not 1 per second, maybe 2 per second? Yeah? Yeah, maybe 1 or 2 per second. So, we'll say the frequency is 0.5. Every half a second, sorry, wrong, big T. Every half a second I hit the ground. So that's my time. Frequency is 1 over T, which will here equal 2. Now I want the omega. Omega, what's the formula? Is 2 pi over T. So that would be 6.28 over 0.5. So that's roughly 12.5. We'll just say 12.5, okay? So I'm walking, and what's my omega? 12.5. So if you build a bridge, you definitely do not want the molecules inside of it to have omega equals 12.5. Why not? It'll break.
But still, they were like, when the parking forces.
Yeah, you're right. This has happened before. So, as you notice, when army troops walk, they all walk at the same frequency. So, it has happened before. Army troops go over the bridge. They all walk with 12.5. The bridge is 12.5. It starts to shake, and no more army troop. Okay? But it's not just with bridges. Okay, you could have it with cars. So you know your car vibrates. Yes? So it'd be really, really bad if your car's vibrating and then there's another part of the car with the same omega. So when you turn the engine on, one part of the car vibrates and then the other part of the car starts to vibrate also, because the omega is the same. So you probably want all the different parts of the car to have a different omega. That way the vibration doesn't spread throughout the car.
That's the bad thing about Russian cars.
It's all the same, is
They
it?
don't know what to do.
Yes.
It's all the same. You just do.
Yes. Yeah. Yeah, because maybe the entire car is made out of the same material. So you actually do want different materials in different places, because you want to keep the vibrations contained. You don't want them to spread out. Yep.
How does the hammer break a bridge?
I invite you to go to YouTube. In fact, I'm pretty sure Mythbusters have done this.
Hammer makes it.
Yeah. Type in
This one on the breaks and break.
Well, there was no one on the bridge, firstly. It was an experiment. But go to YouTube and type in hammer destroys bridge or something.
How to destroy the
How to destroy bridge. Yeah, I've seen the video. It's not a big bridge. It'd be a pedestrian bridge. So it'd only be about 1 metre wide. Okay, but it was a steel bridge. And there was a little hammer, a little machine at the centre of the bridge, and it just kept banging at the bridge. And then as you watch the video, the bridge starts to swing more. Go look it up on YouTube. You're familiar with YouTube, aren't you? Okay, great. Let's have a look. Yeah, but I want to tell you what the homework is.
No, God. Surprises.
Surprises.
Keep it a secret.
All right. Page 80.
Oh, well done.
Yeah. Just one chapter left to do, which we'll easily do tomorrow. It's not that big. And then on Thursday we'll talk about revision.
Which how does it go?
Just energy.
But that here, like, we don't have time for it.
No, it does not mean that tomorrow. So page 80, please. Joshua, mark these questions on page 80. One, two, three, four. Yeah. Yes. Yeah.
That's enough.
Shh. Quiet. Let me see. Figure 9.28. What's that? Oh yeah. Damped.
1, 2, 3, 4.
Shh. 1 to 8.
1, 2, and 8.
Thank you, Mr. Steve.
1, 2, 3, 4, 5,
So
6,
kind.
7, 8.
So
I
generous.
want to edit.
Oh my goodness.
Jenny, should we try to run back?
From number 1 until number 8.
So let us do at least until number 5 for tomorrow.
Oh, what time?
Yeah.
Number 10. Looks nice.
Oh my
7 is like quite long.
No, hang on. I'm thinking. I tell you what, yeah, we'll split this into 2 halves and we can do some small right? But I'm going to change it then. So it's going to be 1 to 10, but you can do 1 to 5 tonight, and then 6 to 10
Next
tomorrow. Yeah.
No, instead of 8 today, we're doing 5.
Yeah. It's more manageable.
We're not doing number 8, which is wrong.
And 11 looks like some Excel questions, so we won't bother with that.
Did anyone do the homework for ECP apart from Rachel? We have to do the research for the